Okay, so in this video, we're going to look at an application of integration in physics. So our problem given is find the force on a half circular window at depth h. Give answers in terms of rho, g, r, and h. So the first thing to do here is to draw out our situation and understand what's going on so we can understand how we're going to use integration in this process. So first, we have a situation where there's a half circular window underneath a bunch of water. And so you can imagine this is like one of those underwater hotels where they have like a glass dome and you get to sleep and watch all the fish swim by. And if you'll notice, in our ocean, we have a shark. So people don't want this glass to break and the shark gets in where you're sleeping at night. And so we need to figure out the sort of force or how much force is being pushed on this glass window so that the people that make glass windows can make them strong enough so the shark can't get in. So that's the situation I imagined when I was given this problem. And so we need to know a few things. So first, if we're going to do anything, we need to create a coordinate system for this situation. So I just put the bottom of our ocean as the x-axis. And then I chose for the y-axis the exact center of this half circular window, because then we can just use our regular circle equation in order to model this, and that makes it very convenient. We don't have to move the origin around. So that I just picked for convenience. So our half circular window, we're looking at the upper half of our equation for a circle, which is x squared plus y squared equals r squared. R is the radius of any size. And so here I have labeled this is the radius. You can see that. Okay. From the answer, the depth of this window is h. H is just a constant given. We don't know how much it is, but it's there. So I've labeled that. And then for the purpose of integration, I have our representative element here, but we'll talk about that in a minute. Okay, so now that we understand what's going on, we need some equations from physics. And the book gives you these equations. It doesn't assume that you've taken a physics course and that you know what these are. And so they kind of just magically appear. And this is the equation for pressure. So pressure is equal to dF, which F is representing force, over dA, A is representing area. Which is also equal to rho times G times D. Now, rho stands for the density of water. That's a known constant. G stands for gravity. That's also a known constant. But if you'll notice for this question, we're just going to leave those as their given letters. So we're going to leave them as rho and G. We're not going to bother calculating the actual number. And lastly, D is the depth. And now when we think about this, so that's the depth under the water. So from the surface of the water to wherever, at any point, that's the depth. And so to this point here, that's H, right? But it's going to vary along this semicircle. The depth is going to vary, so that's something we're going to need to account for. So if we look at this, we have P equals dF over dA. So that means that dF is equal to P dA. And so if we want to find the force, that's what we're looking for here, the force exerted on this window, then we just integrate both sides. And if we integrate both sides over here, we get the force is equal to the integral of P dA. Okay, and this integral is going to be over the region we're working with, and so we'll figure out the bounds for that in a second. And so now we've got P dA. It will help us if we rewrite P as rho times gravity times the depth. So now we have the force is equal to the integral of rho times gravity times the depth dA. Okay, so as I mentioned, rho is the the letter for the density of water, and this is gravity. So those are constants, and when we go to integrate this, we can actually pull them outside of the integral. But we need to figure out what d is, and we need to figure out what dA is. Okay, so first let's do d. So d is going to be the depth, and like I said, that's going to vary depending on where we are along this semicircle. And so if we want to find the depth at any given point here, it's going to be h plus r. Oh, let me use a small r since that's what I have. H plus r, so the height plus the radius, right? That's going to be the total depth from the surface of the water to the bottom of our ocean. And then we need to subtract something for whatever point we are along this semicircle. And so that's just going to be minus y. Because if we're like here, whatever y value that is, that's what we're subtracting from our h plus r in order to find the depth at that exact point. So our depth is h plus r minus y. Okay, so now that we found the depth, we need to find what dA is. So for that, we're going to go back over here to our picture to understand what's going on. So dA is this minuscule little area of our representative element. So first, let me explain why we're picking horizontal rectangles instead of vertical rectangles. So sometimes this matters, sometimes this doesn't. But we want to think about the situation that this equation is in. And so when we think about the force of the water, there's a couple of things we know about water pressure, and one of them is that the closer you are to the surface, the less pressure there is, and as you go further and further down, there's more pressure. So that means that it varies with depth. So depending on the depth, the pressure is going to change. I'm sure if you've ever jumped into the deep end of a pool, you've experienced this. When you go down really deep, you start to feel pressure on your ears. So that's what we need to be representing in our equation. So if we picked representative elements that are vertical, then our representative element would not be something constant. If we had a vertical rectangle here, then the depth at the top of our rectangle would be different than the depth at the middle and different than the depth at the bottom. And so the pressure would be changing throughout our rectangle, so it wouldn't be a good representative element. So that's why we've picked horizontal, because our width here is a dy, which is just infinitesimally small. So that's not going to change. And across it, if it's level, it's all at the same depth. And so the pressure is constant across this whole rectangle. So that's kind of the idea behind why we picked why we're integrating with respect to y instead of respect to x. And I know normally we integrate with respect to x, but you can do it either way. In this case, we have to do it according to y, with respect to y, because that's the way that the pressure will be constant across our representative element. And so we're going to use this representative element to figure out what our dA is. dA is just the area of this tiny, tiny rectangle. And so to find that, first, from here to here is just going to be x, right? That's whatever our x value is at that point. That's the distance from the y-axis to the outer part of the circle. And so the length of this rectangle would be 2x, and then the width is dy. And so our dA is 2x dy. But like I said, here we're going to integrate with respect to y. So when we set up this integral, we want everything to be in terms of y. So I need to represent x in terms of y. And so to do that, I'm just going to use my equation for a circle here and solve for x. And so I will get 2 times the square roots of r squared minus y squared dy. And so that's what my dA is. That's the area of this tiny, tiny rectangle here. So now we can finally set this up. So we have that the force exerted on this semicircular window by the water above it is the integral of rho times gravity times the depth, so times h plus r minus y, dA, so times 2 root r squared minus y squared dy. And then lastly, we need to make sure we have bounds, and so our bounds are between 0 and r, because r is our radius, and so the highest point we get is r, so from 0 to r is our bounds. And so now we can integrate this to find the force in terms of the variables that the question asked us to find. So you can see this, once we work it out, it should just be a simple u substitution to find the answer. So the actual integrating here is not going to be too complicated. It's mostly the setup that's very difficult to get here. So we need to know a couple of things in order to set this up. One, we need to have a good picture of what's happening so that we can set it up correctly. And we need to know this equation from physics to help us figure out what the force should be.